Now if I start from same omega equal to 0, and this time if I travel in anti-clockwise direction, then the negative imaginary axis will be omega equal to minus pi by 2. So if omega is equal to minus pi by 2, then r e raised to minus j pi by 2 will be nothing but minus jr, and minus jr will correspond to negative imaginary axis, which is this. So omega equal to minus pi by 2. So any point lying on negative imaginary axis will have omega of minus pi by 2. And if you go further, then you will coincide with the negative real axis, and hence pi or minus pi both will be equivalent frequency values. So the concept of digital frequency is related to the angle which you traverse in z plane. Whenever you travel in anti-clockwise direction, the angle is taken as positive, and whenever you travel in clockwise direction, the angle is taken as negative. And this gives us one very important thing. It gives us the range of omega. Please remember that the range of omega, which is a digital frequency, is minus pi to plus pi, and sometimes it is also written like this: omega belongs to minus pi to pi. Square brackets means minus. If I include minus pi point, then I have to exclude pi. Or if I put a round bracket here, that means I'm not considering minus pi, and then I'll put a square bracket here, so I'll consider pi, because you can see pi and minus pi, they turn out to be the same values. So omega has the range minus pi to pi. Now what will happen if you keep on taking rounds around the origin? So if you take one more round, you will go beyond pi, and you will take values like pi, 1.5, 2 pi, etc. So minus pi to pi is the unique range of omega, and we should never go outside this range. Even if you do that, then the values of the signal will simply repeat. So that's because of the periodic nature of omega. So this is the relationship between z domain and frequency domain. Now let us complete this whole thing by defining something called as DTFT. So DTFT of x of n, DTFT stands for discrete time Fourier transform of x of n, can be obtained by putting z equal to e raised to j omega in x of z. So x of z, we had defined x of z as summation x of n into z raised to minus n. So let's verify this fact. If I replace z with e raised to j omega, I get x of e raised to j omega, which is equal to summation x of n into z is e raised to j omega, so e raised to minus j omega n. This minus n comes because we already had minus pi as the power. So this is what I get. N will be equal to minus infinity to plus infinity. So you can see there is a relationship between z domain and frequency domain, and that relationship is that z is equal to e raised to j omega. So this is the important conclusion. So if I replace z with e raised to j omega, then I can convert z transform to corresponding frequency domain, which is called Fourier transform. The frequency domain is called Fourier transform. So if I want x e raised to j omega from x of z, all I have to do is put z equal to e raised to j omega. And most of the times, instead of writing x e raised to j omega, I may simply write it as x of omega. Please note that the range of omega is from minus pi to plus pi, and the unit of omega is nothing but radians. That means omega is measured in radians. Whatever value omega takes between minus pi to pi, it will be measured in radians. So like analog frequencies, digital frequency omega also takes negative values. That is because of the Fourier domain representation. We would be mostly interested in the range of omega from 0 to pi, because we will soon prove that for most of the practical systems, if I know the nature of the signal from 0 to pi, that will be sufficient for most of the cases.